Welcome to Abstract Synthesis, where we share the stories behind interesting academic papers in the world of program synthesis. Brought to you by AGI Research Lab and DIA, I'm your host, Brian Landers, and today I'm excited to speak with the author of a really cool paper called Synthesizing Visual Concepts as Vision Language Programs. You might recognize her actually from our recent episode where we recorded live at NeurIPS 2025 in San Diego, California. Can you please introduce yourself?
Yes. Hi, Brian. It's good to see you again. My name is Antonia Wüst. I'm a PhD student at TU Darmstadt in Germany, and I'm with the AI/ML lab supervised by Christian Kersting. And my research focuses mostly on abstract visual reasoning, trying to do inductive reasoning, concept learning from images. And that's why I'm also interested in program synthesis to do the reasoning part of the concept induction and trying to combine it with the visual world.
I'm so excited to dive into this. I feel like you kind of cover very exciting topics right now in the field. Tons of visual perception. We're flooded with videos and images and video creation, Gen AI tools. So being able to reason on top of like this visual content seems very, very valuable and just sort of enticing as a field of study. So I hope to, I'm going to learn a lot today about, VLMs, vision language models, and other things. So thank you in advance for taking me on a tour of your world. I want to hear more about the lab you're working in. Can you tell us about kind of the environment and the sort of energy there where you're studying?
Yeah, sure. My university has a big focus on computer science, and the professor I'm working with, Christian Kersting, he also has been there for quite a lot of years and studies AI. The research focus of my professor is on reliable AIs, but we are quite a big group, so we have a lot of cool, interesting topics we work on. It's about neurosymbolic AI, but also safety, time series, and causality, so a bit of everything. So it's quite cool that you have a quite diverse field, and in general I think we have a quite fun environment to work in because there's a lot of motivated people, and also PhD in Germany is quite well paid, so you don't have to worry about stuff like that. We also have a recent program where it's called Cluster Initiative, where we got funding for reasonable AI. So there's also new PhD positions there, and I think it's developing a lot in the recent years.
Reasonable AI, like as in reasoning, or just like kind of a safety, interpretability kind of aspect?
All aspects of that, actually. So more on the neurosymbolic systemic side, but also on safety and also continual learning and also cognitive aspects of AI. So quite a lot of fun topics.
Very cool. Continual learning, I keep hearing about. Super hot topic.
Yeah.
Well, this sounds wonderful. What a great place to explore all these things you're digging into. Kind of what we like to do on episodes is feature a specific paper just to kind of anchor our conversation. So I mentioned, this paper, Synthesizing Visual Concepts as Vision Language Programs, at a very high level, just to kind of put us in the world that we're going to discuss today. Can you share more? What is this paper about, and why do you think it's worth checking out?
Yeah, sure. So the general idea is that we want to combine the visual perspective abilities of vision language models together with the reasoning abilities of program synthesis, so that we hopefully get the best of both worlds, that we can have the VLM that tells us more about what is going on in the image, but then the reasoning part is done by a program search that tries to find the best program that fulfills the task that we have at hand.
Well said. That seems very, very simple. There's an example you use in the paper. Can you share kind of this idea of like what is the computer trying to recognize, and where does the reasoning part begin? Can you share that example?
Yeah, sure. The task we're considering is induction of concepts in the visual domain. So let's say you have a ground truth concept. It could be, for example, that you have a cake and candles on top of the cake. And this is the ground truth concept. And then you are presented with a few images that are labeled as true examples of the concept, and also some images that are negative examples. So the negative might just have a cake or just candles or just some random image that has nothing to do with cake and candles. And the task now is that given just these few images, where some are positive and some are negative, can you figure out what is the rule that is dividing those images? And there is the part where you have to do the reasoning. You have to understand, okay, what concept is only true for the positive images? And this is actually quite challenging still, because if you give such a task to vision language models, so some of the state-of-the-art models, present them with these images and ask them to solve it, what we see is that they often come up with rules that just seem maybe right on the first look, but if you really try to verify if it's really true only for the positive images and for the negative images, we saw that often those rules were also true for some of the negative images. So
I see.
Definitely not the correct rule. And for this problem, we need something a bit more reliable when it comes to the reasoning.
This is really cool. We're going to dig in more on this. It sounds like, VLMs, very impressive, but they kind of fall down when there's, almost following their own rules that they create to kind of identify, concepts or, just sort of, what the meaning of images is. So called in the reinforcements with the symbolic AI, which is really exciting and what we focus on. What's the story behind the paper? Have you been working on it for quite a while? Was it a quick journey writing it? Tell me more about the genesis of the paper.
Yeah, I think it goes back already to my first paper when I started the PhD, because there I was already looking at visual concept learning and inductive reasoning based on images. But back then we were looking at synthetic images and had a pre-trained object detection module. So we were looking at clever images as part of that. And there it's quite easy to train a neural network that just tells you how many objects there are, where they are, and what kind of attributes they have, like color and shape and so on. And with that, based on that, it was quite easy to use this as an input for program synthesis. And we saw that when we learn programs based on this representations, this was generalizing way better than other neural baselines. So we were using the program synthesis to already solve visual concept induction tasks, but in clever images.
What is, just so I'm not familiar with clever images, what's that?
Yeah, sorry. It's a quite typical image data set, and they also have a generation. They have the generation code with Blender online, so you can also create your own images, and it's always a black background with some colorful objects in the front, and then they can have different shapes and colors and also materials. And so you can very systematically create tasks with those images, because you can define yourself how many objects, which colors, which positions, and so on they should have. So they're often used for rather logically challenging visual concepts. Yeah.
Gotcha. Is it used often for like training large language models, I'm guessing, or VLMs in this case?
Yeah, I'm actually a bit curious about this, because a lot of the benchmarks have clever images where you need to do more stuff like counting and maybe also spatial relations. But what I saw when I did tests with those clever images and vision language models was that sometimes, for example, with counting, when you have a clever scene with 10 objects, the VLMs were really bad at counting those objects. They would sometimes tell you, okay, there's 10 objects, there's 9 objects, there's 11 objects. And then when you want to count how many red objects are there and stuff like that, it was really not reliable what they produced. So I'm still wondering a bit how much of them is included in the training data, or if maybe the counting itself is still very hard to do reliably. Yeah.
This makes sense. And so you kind of discovered, this symbolic side, using program synthesis, what was helping sort of, those other, libraries or whatever you call them. And then how did that lead to this, the paper that we're discussing today? Was it sort of like, okay, there's something really cool here. What's another challenging problem to pick? How did you kind of go about picking the topic?
I was always a bit dissatisfied that we had the pre-trained object detection. So it was always in the back of my mind that I wanted to make this approach more general. And of course, you always also get the feedback, okay, what about real-world images? How can it translate to that? So it was still in the back of my mind, but then I got a bit distracted by the Bongard problems. I don't know if you heard about them, but it's also, again, visual inductive reasoning, and but they are based on black and white images. So the diagrams style where you have, for example, a triangle drawn or a square drawn, and then a visual concept could be that there is a triangle versus a square, or also more complex stuff that there's more black circles than white circles. Also a bit weird shapes sometimes. So, for example, there were also weird spirals, and then you need to understand that there's spirals turning clockwise or counterclockwise.
Tricky.
So these kind of problems, and they're actually quite old already. So I think from the end of the 60s, and they are not solved until today by AI systems. But back then I was quite motivated and thought, okay, I have this cool program synthesis approach now. Maybe I can apply it to the Bongard problems and solve them. But when I was thinking about that, I was already thinking about using vision language models for this, because it was a time where they were coming up and seemed like they can do cool stuff. But what I was realizing was that when I provided the Bongard images to the VLM, that oftentimes they struggled quite a lot to understand what's going on in the image. So, for example, with the spiral example, they would just give random answers, whether it was clockwise or counterclockwise turning. So, and also spatial relations were quite hard. So I had to realize I can't really use them to solve the problems. But we still figured out that it's quite an interesting finding. And then we also tried to make the vision language models solve the problems in general, and to see how good they are performing at it. And it was quite interesting, because sometimes the perception was an issue, sometimes the perception was working well, but then the reasoning was an issue. So we collected these findings and made a paper out of it, and making people aware, okay, look, there's this cool problems, and they are quite understandable for us humans. So we showed also that humans can solve the problems. Some problems are easier, some are harder, but generally it's interesting to see that these problems that we humans are good at solving are still quite challenging for the vision language models.
Yes.
So, I got a bit derailed by that.
Yeah, that's a big driving force behind, ARC Prize, the work with the ARC AGI benchmark we do, is just that gap between, what's easy for humans and what still remains hard for AI. Because it kind of shows us the sort of, the remaining, the path that we have toward solving true, human level intelligence. So I'm totally with you on that. And you kind of saw that gap there.
I'm super excited about these topics, or this gap as well, and understanding how we can maybe close it a bit, or what are the problems on the way there.
Absolutely. You mentioned who are your co-authors with this paper? Was it anyone else? Was it primarily your work? Tell me more about the team behind the paper.
Yeah, my one of my co-workers is Wolfgang Stammer, and I worked already with him on my first paper that was using program synthesis, and he was actually my master thesis supervisor, so we always worked quite close, and he's more from the concept side, so he's generally studying a lot AI systems that can learn concepts and then reason about those concepts, but so that fit quite well with the program synthesis stuff that I'm doing. And he's at Max Planck now, but we still collaborate. And then I was also, I think in the beginning, when we started the paper idea, it was mostly Wolfgang and Hikaru and me. Hikaru is another colleague of mine, and he's more from the inductive logic programming side. So he has nice work on inductive logic programming with neural networks, trying to make it differentiable and combine these things.
Right. We just spoke with Andrew Cropper, creator
nice.
of Popper for the ILP world. So we learned about that. Very cool work.
I feel quite honored to be in line with all the great people you're speaking here at the podcast. So
you deserve it. You deserve it, my friend. I think you just getting started too, and your work is. I'm telling you, this vision stuff is like really exciting to people.
And also, Lucas joined in data in the project. He is working on reasoning as well, more on the large language model side. And I think that might also be interesting. We have a paper that we worked on recently where we are looking at the SAE features in Dutch language models and how we can add logic on top of that. So if you have some task in natural language and some additional information which you can encode in a rule, then you can add this rule on top of SAE features, so sparse autoencoder features that give you more information about the concepts that your model is detecting in your input. And by that, you can apply these rules to the concepts and then also use the information to steer that back to the output. So the cool thing about that is that, for example, if you know that your input there's a tower and you're in Paris and maybe there's also a croissant or something, then you can have a rule that infers there's probably the Eiffel Tower, but maybe your model doesn't know about Eiffel or doesn't activate for Eiffel, but your rule is telling it that it should activate, or vice versa. If you have a bridge in San Francisco, then it's probably the Golden Gate Bridge, and things like that. But that can also be interesting for safety aspects, so that you can encode more complex rules that are related to safety things. So what is safe and not safe, and feed that back to the model.
Yeah, that whole angle is, that's sort of been the domain of, AI pre-transformers, right? Facebook kind of, Instagram kind of making sure that like there's, safety and, sort of automated curation and things like that,
Yeah.
I'm dying to hear more about the paper, but I think I need a little bit of a primer on just, vision language models. Like, have these been around for years? You mentioned kind of state-of-the-art ones, which I'm sure are kind of, being developed in the field now. And there's some kind of like failure modes, which sort of inspired the paper that we're talking about. Can you tell me a little bit more about VLMs?
Yeah, definitely. I think they emerged, I'm not sure which year exactly, but I think for a few years they are around already. And I think it started when large language models were proven to work quite well, that people were thinking about, okay, now that we have the text embeddings and can do cool stuff with that, can we maybe incorporate vision as well? And there's a lot of work that tries to combine the latent space of text with the latent space of images. So trying to see, can there be an embedding learned that can be decoded to text and images as well, so that you can have one embedding that can capture the meaning of text as well as images. And I think there's still a lot of work going on how to combine text and vision in the best way in vision language models. And so I think it's not done yet, but at least it's working quite well already when it comes to captioning and just high level understanding of the images, I would say. But what I think is still an issue with the models is that if you want to be more detailed about your image, or you want to have specific spatial relations, or like I said before with the spiral shapes, when you want to understand if your spiral is turning clockwise or counterclockwise, that is still quite a challenge for the models. And then there's also the problem, what happens when you have multiple images? How can you really understand the context across multiple images? And also, if you have to do reasoning tasks, how can you reason playfully about it? So I think there's still a lot of challenges for the models, but still there's also already a lot of impressive stuff that they can do.
Yeah, I just have to say, like, how cool is it that like language and, embedding, latent space, like can even at all in any way relate, have results in a visual domain? Like that is just kind of seems pretty darn cool to me.
Yeah, totally.
These are some of the known issues with it, and you had discovered, hey, this symbolic work, specifically program synthesis, is yielding some interesting results, and that led to this creation. I mean, tell me if I'm wrong, but of vision language programs. What sparked that idea? Was it just kind of going, I have these tools, let's test out how it improves the results of VLMs? Or was this kind of like a vision that came to you, like a lightning struck you and you went, vision language programs, like we need programs, not just prompting,
Yeah, I think I was always fascinated by program synthesis because I think it's a very powerful tool that, based on some input-output examples, you can just start a search and the search will give you the best program for your constraints. And it seems also like a very reasonable approach to inductive reasoning tasks. And in comparison to when I think these reasoning abilities are the things that a lot of researchers try to get into vision language models, but it seems like so much work and so much additional tokens and reasoning traces and so on to get to a result that can be achieved maybe way easier with program synthesis or in general search-based algorithms. So I always had the feeling, okay, this kind of reasoning task should be easier solved with symbolic search than trying to put really everything into the model and try and try again, prompt the model. If it's not good enough, then you just
more
prompt
tokens
again and again and hope that if you change your prompt, maybe your result will be better and so on. It seems very tedious to me. So I felt like there's probably a better solution to it.
I think you kind of proved you were right. So not to give away the ending, but you were right. So you explicitly don't put the sort of reasoning stuff inside the VLM. That was sort of the sort of challenge. Was it interesting sort of figuring out where the dividing line was, like where the sort of reasoning type tasks, like that was it a clear sort of separation, and was that separation seems like it was super important to the results?
Yeah, I think a lot of the separation comes quite naturally from what is the part that is perceiving and what is the part that is reasoning, because the perceiving is mostly, okay, is there something in the image or what is in the image? And the reasoning part is then asking about existence in the set of objects or counting and stuff like that. I think there's somehow a natural division. But in the beginning, I was also considering asking about all the existence individually. So is there a cube? Is there a blue cube? Is there a green cube? And so on. But then we quickly realized that this is not so, it doesn't scale really well if you have to ask about all the object combinations and so on. And that's why we have a bit of a intermediate step in the process, so that you don't have to ask about all the individual objects and prompt for that every time.
That's cool to hear that it sort of, was intuitive, the sort of separation of those things. That's wonderful when it works out like that. All right, you were kind of alluding to, vision language programs, VLPs, have this sort of 3 stages, I think you could say, kind of the processes, which the paper goes deep into. Can you break it down for us? So there's like symbol grounding, I think is the first one, DSL, grammar, and then lastly, synthesis. Can you tell us like what happens in each of those stages?
Yeah, sure. In the beginning is we have the symbol grounding, which is an important step, I think, because here we are looking at the complete task. So let's say you have 6 positive images and 6 negative images. So you're looking at all these 12 images, and now the question is, okay, what might be important about these images? And for that, we are using the vision language model to give us the first set of elements that we can talk about, because that's also important for the programs later. They have to have some symbols that they can use. And so here we are asking what objects are relevant in these images, what properties do these objects have, what actions might be displayed in the image. And why I think this part is important is that also sometimes for a concept, the context of the other images is important. For example, if you see an image of a house at daytime, you might not consider it to be important that it's daytime. But if you see an image of a house at nighttime together with the image at daytime, then you will understand, okay, maybe something about daytime, nighttime is important. And so I think it's always important to have these contexts in mind when you have visual concepts, because sometimes nuances are important, but sometimes it's just something about a house, but you only know it when you see then maybe another image of a small house and a tall house, and then you can understand, okay, maybe it's about the size and stuff like that.
That's so cool. And humans are just so good at this stuff, right?
Yeah.
That's fascinating. Really cool. I like also that it can be actions. It's objects, properties, and actions are what symbols can kind of represent. It sounds like a lot going on in that stage too. Just, what symbols are allowed for a task and what are important. Seems like a lot of work can go into kind of figuring even that. Because if you don't have the right symbols, I'm guessing it doesn't really matter like what amazing probabilistic context-free grammar you create, or the programs you synthesize won't be relevant to the inputs. So it does seem very important.
True.
So the VLM wins that phase, it seems like. Yeah.
And also an important aspect is that now you have defined a context that the programs can talk about. So you can also be sure when you then ask later in the DSL, there will be functions that will call a VLM with just a single image. And with this context, you can make sure that the VLM knows what to look for in this individual image. So when we want to know really for the individual images what is displayed in them, to then be able to reason about it, then you make sure that the VLM knows what to look for the single image. So for example, for daytime or nighttime stuff, yeah.
All right, so that's stage one. Stage two is this DSL and the kind of grammar needed to synthesize programs, I guess, right? So what happens in the second stage here?
Because we want to have programs that can operate on images directly, an important aspect is, of course, how can we execute a program on an image. So what we did is that we defined vision language model functions, VLM functions, that are basically prompts to the VLM, but they take in as input an image, but also the context, as I said before, so the symbols we discovered in the symbol crowning phase. And then it will output a symbolic representation of the image. So that's a bit where the magic happens, where we're providing this interface from the image to the symbolic world. And this is an important part of the domain-specific language. And then when we have this symbolic representation of the image, we can then just have functions that can be executed on it. The image we have two kinds of symbolic representation. One is an object property representation. So we have a list of object property pairs or tuples. And then there's another symbolic representation where we have the action object representation. So one where it's just about the objects and one where it's also about the actions. And based on these representations, other functions can be executed on top of that. And then those are then responsible for the reasoning part. So for example, checking, does there exist a dog or cake or whatever in this symbolic list? Is there more dogs than cats, or things like that can then be executed on it. But here it's now really just symbolic functions executed, and it's not the job of the VLM anymore.
Are these, the sort of rules being created here, is that automatically discovered? It seems like just a gigantic search space. I guess they're guided by the symbols that came out of the VLM in stage one, but how do you limit it down from there in terms of creating this, the DSL?
Yeah, I think the limitation by the symbols is quite an important part of it, because if you would have an open vocabulary and would need to ask about all possible concepts or objects and so on, I think that would
Yeah.
be quite tricky. But
Yeah.
yeah, by limiting that, and if you think about it, it's not that many functions actually, because you have the two VLM functions, then you have a few symbolic functions that ask for existence and counting and equal and stuff like that. And
Uh,
we also limit the depth of the concepts or of the programs, which are then the concepts, to 5. So it's also not a super deep search. And we saw that this works actually quite good to learn visual concepts already, because the usually real world concepts are not that complex. So usually there is a cake and there's candles, for example, or there's uh, either a large cylinder or a small square or cube. So the concepts that are usually looked for are okay from the size. So what we saw is that by combining those two things, we actually don't have that big of a search space.
that's surprising. That's really cool that just that few results in powerful programs. Okay, and then there's this piece, and I'm not super familiar with this, but I mentioned it before, the probabilistic context-free grammar. What makes it probabilistic? Why does it need to be context-free? Can you break down kind of the part of the grammar for us of this second stage?
Yeah, that's a part that is often used during program synthesis. Actually, the implementation is based on another paper, which is, I think, called Scaling Neural Program Synthesis, something like that, von Nathaniel Filiaco. I have to check the name.
We'll include it in the show notes. So
Yeah,
look there for the link.
yeah, and there they were proposing a method of as searching based on neural networks that learned a distribution over the program parts in the domain-specific language. And we use their code, but actually what we found was we don't really need to learn the weights, because the information we get from the VLM is already sufficient to search space without a lot of guidance. So we are actually using just a uniformly initialized grammar. But what we do is we weight the symbols a bit by their appearance in the task images. So for example, if a symbol like dog appears only in the positive images and never in the negative ones, then we give it a higher probability than something that only appears in a few negative ones, or something that appears in both sides of the concept. And
Okay.
theoretically, you could still extend the work and learn distribution of other primitives, but we found that by using the prior knowledge of the VLM, we didn't actually needed this, and the search space was manageable enough to just search it as it is.
That is so cool. I'm learning a lot about counterintuitive things, like the real world, sort of symbol recognition not needing to be as deep a search as you'd think. So I think we got the second stage pretty well. And then comes the fun part, which is synthesizing programs, which hopefully can create outputs that sort of follow the rules, including like the sort of conceptual logic of these inputs. What happens in that stage?
So for the search, what we do is we just formalize the problem into an input-output example problem. So you have the images, which are your inputs, and then you have a Boolean output. So whether it's a positive or a negative example of the search. And then you can just start to search for programs that can map an image to a Boolean. And because you have the input-output examples, you can just check if a program that you found is fulfilling your task constraints. And what we do here is that actually we also consider programs that don't have perfect accuracy on the task examples, because of course it may happen that the VLM has a wrong wrong interpretation of one of the images, or that there happens, or did it oversee something. It doesn't happen often, but it can happen, and to still have a program at the end that might be still correct or might be at least close to your solution. We also keep track of these programs, and then we'll output at the end the best program. So because sometimes that was also a problem in my first work. Sometimes the program synthesis wouldn't find a program, and then I think it's better to take a program that is at least partially correct or almost correct than not having anything at all at the end.
Yeah, and if you put that in kind of a loop, you could sort of have, learning start happening and stuff. So you kind of learn from failure, right?
Yeah, exactly. You could maybe even loop that back to the VLM and say, okay, maybe this concept is relevant. So can you take a look again at the images and see if you might find it in the one image that was misclassified or something like that. So that's a fun part. You have a lot of interpretability given by the process. You can actually look at the programs that the model found, that the search found, and judge for yourself if you think it's correct or not.
Okay, so a big question, everything we've said so far, the VLM kind of succeeded and found the right symbols and concepts. When that fails, when it doesn't succeed, I mean, we just were explaining, future versions of this could kind of loop around and have multiple iterations. But as it stands in the paper, what happens if the VLM fails?
It can have different origins. So one problem, I think you mentioned it earlier already, is that maybe the VLM doesn't find a relevant element of the concept. So if the concept is about pets, for example, but the VLM just tells you that cat and dog are relevant, then it might happen that you also have birds or
I don't
fish
know what else. What are other big pets? Yeah, fish. I was about to say pig, but there's only a couple of people that have pigs as pets. But anyway, it is. Yeah. Let's go with fish.
Yeah. Then the VLM wasn't able to, or didn't propose you this abstraction of the objects, and then it's harder to find a rule. Of course, you can still have a program that asks about dogs and cats, but if your test image has a bird, then you're not able to classify correctly. So these are things that can happen. Also, what we saw sometimes was with, again, the clever images, so the synthetic object images, that sometimes the property size was not detected by the VLM or maybe not considered relevant. So the VLM would interpret the image and give you the objects and the colors and maybe the material, but not the size. And then one or two of the rules were about size, but then the programs were not able to talk about it because it was not in the symbolic representation about the image. So these are problems that can occur. For example, with the clever example, it was still able to find part of the rule, just not considering the size, which was also important. So at least you still get some output, and can maybe, as a human that judges the result, can act on it. And that's actually an example that we had where we added additional VLM functions that were explicitly asking for the size of objects. And by adding these functions, we were then able to solve this problem way better. So we're able to find a ground truth rule with that. So that's also a cool aspect.
This makes sense. It's kind of, this is a domain and it has some known kind of things like attributes of objects, for instance. And so that just makes sense to kind of cook that into the process. You did a great job in the paper, sort of, testing things and coming up with actual results. Sort of evaluation-wise, did any of the benchmark results surprise you in any way? Or did it all kind of match your intuition on what would happen?
I think some parts that surprised me quite a lot, even though, I mean, it makes sense, but sometimes it's really cool to see that just by providing the images and not providing any more details for the task, that the method was actually able to find a program, also complex programs that were representing the ground truth rule. So it feels a bit like magic. You just give some images and then you get a program as output that tells you exactly what's going on in the images. So yeah, I'm still super happy about that it works. But yeah, sometimes interesting stuff comes up. For example, sometimes there's a program and at first you think, no, it doesn't really make sense. But then if you look at the images again, you understand, okay, it might actually be true for at least some of the images, or sometimes there's shortcuts that are detected by the programs because you only have so few images. Then it can happen that the problem is a bit underspecified, so there might be multiple solutions, and the program search always leans also towards more smaller programs. So for example, there's also one task where the ground truth rule was a person holding a surfboard, and then the program that was discovered was just holding. There's the action holding.
Whoa,
But it makes sense because when we looked at the images, all of the images had surfboards, also the negative ones. And the only thing the most simple thing that was dividing the positive from the negative ones was the action holding. And so if there would have been more images, or at least one image in the negative images where there was a person holding a bike or a bag or something, then probably the program would have changed. But with that information, it was correct, even though it's not the ground truth rule there.
Yeah, that is really cool. What's an example of a shortcut? So like, sometimes it's actually like gets faster to the thing. Maybe that's different than like your human, intuition of kind of categorizing things. Can you think of a specific example of that sort of shortcut detection or mitigation?
In general, a shortcut is something that is not the target, or it's not the intended solution to your problem, but it still helps you solve the problem.
This makes sense. In the ARC world, this totally feels familiar to me.
Yeah. So I think one of the most classic examples is an example where you have a dog and a wolf, and the wolf always appears in snow and the dog not. So if you have a dog in the snow, then the model will tell you, okay, it's a wolf, because it was never really learning what is a dog and what is a wolf, but it was always focusing on the background. And so this is actually a quite big topic in other domains. It happens a lot in images. But yeah, as you said, also for arc reasoning tasks. So especially if you have this few-shot learning scenarios with the visual concept induction, it's something that can appear. And I think it's also really important to keep that in mind when designing benchmarks and such tasks, because you want to make sure that your model really learns the rule that you intend, and so you need to make sure that there are not shortcuts that the model can exploit.
That is so fascinating. It's just so interesting. This all happens like in like in machine learning, but I love it. Okay, so big question for you, I guess, kind of coming from this work. Do you see these VLP, like vision language programs, as sort of a stepping stone toward like verifiable multimodal reasoning?
Yeah, definitely. I think it's a good step, and also a reminder that there are methods that actually have some more reliability, faithful reasoning properties than just neural networks and vision language models have. And I was also talking to some people that were more from the deep learning side, vision language models. You just need more data,
Yep.
and everything will be solved. And they were. I had the feeling that they were maybe stopping a bit and thinking, okay, maybe this is actually cool. Maybe there is benefit in using symbolic methods. So I think it's a really exciting direction. And it doesn't have to mean that you move away from vision language models completely. Maybe that there's also ways where you can train the model to understand when to start a program synthesis process and then do the process and then go back to the next token prediction or something like that. So I think integration in other more agentic systems could be definitely an option.
This is exciting. Okay, really fun. I'm getting a little preview of maybe where you go next, which I'm going to ask about. But before that, you mentioned, kind of winning over folks with this sort of, symbolic approach. You presented at NeurIPS, that's where we met recently. How did it go? What was the reaction to your paper and just, these other kinds of, it's so funny. It's older than Transformers, but it does seem kind of like, like the alternative approach now or something, because we went so deep into LLMs. But what were the reactions like at NeurIPS?
Yeah, quite good. I think what a lot of people were quite convinced by was that we also had an experiment where we compared thinking, reasoning vision language models, so the ones that produce these long chain of thought reasoning traces, with our approach with non-thinking models, and we achieved better results, but used so way less tokens for that. And I think that's where a lot of people were kind of surprised and convinced that is a cool approach. Yeah, but I think also got also feedback from cognitive scientists that find this approach quite interesting, because I think it's also a bit like system 1, system 2 combination of models.
The kind of intuition of the symbol recognition, and then kind of like, no, it's got logic and it feels like a program almost that kind of identifies things and then is able to kind of, turn it into the Boolean at the end, like true or false, candles on cake or not,
Yeah.
That's beautiful. I'm really glad. Congratulations on having that, feedback, and just getting to speak at NeurIPS at all is a big honor, I think, right?
Yeah. It was my second time at NeurIPS, and I was so happy that I was able to be there again. And I always enjoy it a lot.
That is so cool. Before we kind of, wrap up here and ask you about what you're going to do next, which is super exciting. I'm really excited to hear where you're going. Is there anything we missed? Like, is there anything people who, are checking out this paper or wondering if they should check it out? What's something that's like really important about it that we should share?
I think one of the coolest insights is that you can actually treat the vision language model more like a function or a tool that you can use in a bigger environment. So I think this aspect is really cool, and I think it has the opportunity to be used also in other neurosymbolic methods. And to see, maybe some people are still also a bit skeptical about vision language models, but you still can use them as a tool. And even if you're still a bit skeptical about vision language models, that you can also use them as a tool in your more symbolic, reasoning-focused work, that they can have a benefit there as well, because they're out there, and I think there's definitely benefit in using the open world knowledge that is encoded in the models.
Yeah. It's like it's so funny. We had Professor Moshe Vardi on a recent episode, and he was saying, just use the tools that are available to you that like, do the perform the task like best. Almost kind of, shamelessly like pick the one that works. Like there's nothing wrong with, it doesn't have to be all one thing, and I think your work exemplifies that.
Yeah, I like his take a lot, and I totally agree. I think nowadays the focus is, like, generally from the community, the focus is more on the vision language models and foundation models in general, and they neglect the symbolic part a bit. So I think it's important to tell them about the symbolic stuff, like you do here. But also maybe for some symbolic people, they are still skeptical about foundation models, and also it's not bad to have a look at them as well.
I do see the sort of bridge between the worlds happening for sure. That's our approach at India, for instance, and I think folks, even like we mentioned, Andrew Cropper, from the ILP world, like also leveraging LLMs to see how far ILP can go, and get better results there. So I think the cat's out of the bag in terms of combining these approaches and sort of the opportunity there. So, but you're definitely a pioneer in that world, especially like in the visual perception side of things. Okay, so tell us, Antonia, what are you up to next? You could keep pulling the thread of improving the results of these things by combining these approaches, VLMs plus these vision language programs. What else could it be? Gosh, I don't know. There's so many ways. Or you could just abandon all that and do something totally new and switch into, quantum or something like that. But you tell us what's next for you.
Yeah, I think that's actually the real fun part about being in research, that there's so many cool opportunities and cool research directions you could pursue. So yeah, I'm also always trying to navigate a bit what is the most exciting thing to do next. I think for VLP, there's definitely some cool additional extensions. So for example, making it more object-centric, that you really maybe have some segmentation first and then do the part where you ask the VLM about the objects and not about the whole image. So I think there's some natural extensions that would be also worth pursuing. In the meantime, I'm currently working on a project where we actually try to combine vision, induction, and also action or experimentation. I think that's also something you're doing at NDR at the moment with ArcAGI3.
Oh, ArcAGI 3. Yeah. So that's part of where you're going with this, is applying it to not just so adding a temporal, sort of aspect to it. So almost like frames of a story or something.
Yes, but the new frames you get are based on what your agent wants to know, because
You got it.
as I said before, you have the images, and sometimes there's not enough information. But when you do program synthesis, you have a long list of hypotheses that might be the ground truth concept, and maybe there's a lot of hypotheses that are true for your current images. And then the cool question is, okay, can you now propose a new image and check, does it and ask an oracle whether it's true or wrong, and then to verify or neglect your hypothesis. So I think this is a fun thing to think about. Yeah.
That is pretty cool stuff. And we definitely love that over on the ArcAGI side, messing with sort of more game-like things, but with agentic AI on the end, deciding what actions to take. There's a lot of work to be done there. Like the out of the box sort of LLMs are not good at this stuff yet. So I'm curious what you'll come up with. But very, very cool. So maybe we'll have to get you back on when you've solved ArcAGI 3.
Yeah. I mean, for now, it's mostly first understanding a bit what current methods are able to do, and see if you have pre-trained modules and so on, how good they perform. But yeah, it's fun to work on these kind of questions.
That is so exciting, Antonia. I can't wait to see what you get up to. I hope everyone will also check out this paper, because it's really exciting work, that was featured at NeurIPS and got all this great reaction. So definitely go check out this work. And just thank you so much for taking the time to speak with us. And I hope to have you on in future episodes. So you'll come back. You're our first. Are you our first repeat guest? You might be. So we'll have to have you become like a regular on the show, but you have an open invite to come back anytime. But thank you so much for your time.
That's so nice. Yeah, thank you for having me, and thanks for your great work with the podcast. I really enjoy it. I think it's a really cool thing that you do.
It's an honor speaking with folks like yourself. So never a dull day, always so many cool things to learn. So we appreciate it. Thank you for your time.
Yeah, thank you.